my work at CMSA Colloquium, and actually I was also the former organizer of the colloquium, so it feels good to come back in another perspective. I apologize in advance that I recently caught the flu. Well, luckily not the dangerous one, but caught the flu. So if my voice is low in the middle, so please forgive me and just point it out. So yeah, I apologize for in advance for this. Okay, so today I'm going to talk about tetrahedral instantons and its relation with M-series index. It's a series of papers work with Ali Pomoni and Xingyu Zhang. So one already appeared last year, last summer, and we're hoping the other two papers in related topics will appear this year. And there are certainly other works in this area, so I will mention during my talk. So since this is a colloquium, so I would like first review some background on instantons. First, when we talk about instantons on R4, we mean the solutions of a self-dual Yang-Mills equation that star f plus or minus f equals to 0, which means plus or minus means a self-dual or anti-self-dual condition. So when we talk about instantons, we're talking about solutions of this equations, where if we introduce parameter n labels the rank of gauge group G. Oh, by the way, this f is Yang-Mills connections. If we introduce n as to label the rank of gauge group G and k to label the instanton number, we can label the space of this solution of this equation as a modular space M, G, N, K, where G is a gauge group. Okay, but interestingly, there is a algebraic construction for this same modular space of this differential equations called ADHM construction. At least for initially it's for A-type case, but now I think it generalized to our classical group. It's called ADHM construction. So this gives the algebraic way of constructing the solution space of the differential equation, and it also uses a hyperkähler quotient. So roughly in the ADHM construction, the modular space is described by the series of certain complex matrices, B1, B2, and this I and K. You can view this B1, B2 as K by K complex matrices, and I and J are K by N and N by K matrices, also satisfying this relation, the relation here. It's the commutator of B and B dagger plus II dagger minus JJ dagger equals to 0, and this and the second relation. Oh, should I? Let me see. Oops. So and the second relation, there is just a B and B without any dagger. So once you have all this set of matrices satisfy this condition, we quotient with the UK gauge group to get the final. To get the final modular space. So this is a brief review of how we use algebraic way to constructing the ADHM instanton modular space. Okay, so there is a nice there's a nice string theory picture for this ADHM construction. Basically, if you consider k instantons in R4, sorry. In string theory, you're considering the setup of k d1 brains inside the n d5 brains. So as I draw it here. And if you look at the word volume effective theory from the D5 brain, this then this strings, then the strings connecting the D5 brain gives the the effective theory on the D5 brain gives the Yang Mills. And then you put the KD1 instanton, and then the strings connecting the D1 instanton and D5 brain, D1 brain and D5 brain roughly gives you the solution. So in that case, all these matrices has certain string theory meanings, and then the moduli space is roughly the Higgs branch. The moduli space is roughly the geometric configuration of this brain setup. But from string theory, there is another picture of looking at this. So if we use the word volume theory of D5 brain, we connect it with the Yang-Mills field equation. But if we an equivalent way of looking at this brain setup is looking at this D1 brain, effective theory of this D1 brain. Then we get a effective description of some two-dimensional word volume theory, and then this we can interpret this modular space M as a Higgs branch of this theory on this of the effective theory on this D1 brain. And then since we have KD1 brain, the effective theory contains a UK gauge group. That's why in the definition of ADHM construction, you have to quotient this UK, because in the effective in the effective word volume theory of D1 brain, this UK acts as a gauge group. So this the second point of view has the advantage of helping us computing a lot of things much easier. So
why is this instanton in SUN theory as opposed to UN theory?
Oh, actually, they should be they work for if we go to this brain picture, it should be the UN theory, where the U1 degree of freedom is the overall position of all these springs, right? It just I was kind of sloppy about this SU and UN.
I see. So the definition above, this hypercube quotient, that's for the UN space.
If you're right, so this case I should change this. I should change this to UN.
I see. Thanks.
Yeah. I have been sloppy about these notations. Sorry. Oh, by the way, how to remove this?
We don't see anything there.
I actually draw a line here too, but okay. Well, that's fine. So the modular space, the ADHM modular space has a problem that it's non-compact. So mathematically, it's a bit it has some trouble to study very well. Then Nakajima introduced a way to resolve this singularity of the original modular space. He called this resolved modular space as M tilde, which you see its definition is for, still this ADHM definition, but the first relation instead of equal to 0, he introduced a resolution which is equals to identity matrix times a parameter zeta. Okay, and then because of this resolution, he proved that the solution has to be I equals this I matrix has to be 0 or J matrix has to be 0. So one of the ij has to be equal to 0. And then the most important relation is that this M tilde is isomorphic to the modular space of torsion-free sheaves on C2. So actually, that's how originally we are considering the modular space of some nonlinear differential equations, but now Nakajima showed that this modular space also modular space of torsion-free sheaves. And then on the other hand, Nekrasov and Schwarz also, oops, sorry. Nekrasov and Schwarz also give a brain setup for this modular space. So originally we in the original setup we just have the D1 brains and the D5 brains. Now, but we know that in string theory there can also have this background B fields. So they show that to get this to obtain this M tilde, you just have to start with type 2B. Type 2B string theory plus some certain non-zero background B field. And then it's clear from the brain setup that this M tilde has certain isometries, that has certain symmetries, which is a U1 cross U1, which belongs to the is a subgroup of the original SO4, which comes from the rotation of this R4, and then they also have this well, okay, it actually should be UN. It's a rotation of gauge orientation at infinity. So on this, once we have this M tilde, one can compute the instanton partition function on this M tilde, which is roughly speaking is some integration of 1 on this resolved modular space. You see, if the original if we integrate this one on original modular space, because M is not compact, there is no definition of this integration. It's only after you resolve it, you get a compact one. Or in original Nekrasov's work, he do a omega, he consider omega deformation to make this one localize, to make this to make the one can use localization trick to compute this thing. So yeah, anyway, once you have this M tilde, you certainly can get this instanton partition functions. And this instanton partition functions, instanton partition function connect to many interesting fields of physics and mathematics. For example, originally, Nekrasov used this instanton partition function to compute the Seiberg-Witten prepotential, and later it's related to A-model topological string, and then by the work of AGT, this instanton partition function are related to Virasoro or W algebra conformal blocks. Then later, Nekrasov and Shatashvili also found that this instanton partition function has a deep connection to quantum integrable systems. So, so this instanton partition function is definitely observable that has many rich applications. But so to have something, so it's very important to compute or given setup to work out the precise form of this instanton partition function. Originally, Microsoft use this put everything on omega background and doing equivalent localization, which we now call it IR, sort of IR infrared computation, which you have to start with your theory and have some knowledge on the infrared theory and then work it out. But later, there are other methods of computing the same instanton partition function, not in the IR, but just treat this as treat the partition function as elliptic genus of certain 2D supersymmetric series. There are many works, related works on this, and including Qumran's work. But one of this review is the paper I list here. Okay, so we refer to this method the UV computation. So this method works. We can compute the partition function as an elliptic genus of 2D supersymmetric series. It's also related to the to what I previously mentioned, that for the same instanton partition function, for the same instanton setup, if you look at branes, you can view this as the word volume theory of D5 branes, or you can also view this as word volume theory of D1 branes. If you use the D1 brane word volume viewpoint, then you get this 2D theory. So the advantage of this UV method is that it only requires the 2D supersymmetric effective series, and there's no details needed for this M tilde. So in fact, without really getting into the full detail of M tilde, one can get the partition function, as we will see. And once you have the partition function, you can also try to find the connection between all these different branches of mathematics. So later, then we also consider, people also consider the generalization of the Yang-Mills instantons in higher dimensions. Remember that recall that what I talked, the standard Yang-Mills instantons are the self-deal or anti-self-deal solutions in R4. So if you consider other brane setup, like for example D1, D7 brane setup, this gives you the ADHM modular space of instantons in 66 dimension. It's actually a solution of Donaldson-Uhlenbeck-Yau equations. And then you can further consider brane setup like D1, D9, and D9 anti-D9 branes. This gives you the so-called magnificent four models. Actually, this was first proposed by Nakajima, and he conjectured that this magnificent four model is sort of the mother of all instantons. In some sense, all the other instantons are sort of related to this one. We will see in our later, we will provide certain evidence of his conjecture. And also this, if you come for this generalized instantons, if you compute the instanton partition function of this resolved instanton modular space, it actually matches the generating function of Donaldson-Thomas invariants on the certain Calabi-Yau 3 or Calabi-Yau 4 manifold. For example, Bonini et al., they actually show that if you in this KD1 and ND7 brane setup on the background of R1,1 times C3 times R2, they consider this background and then compute the partition function. it matches with the Donaldson-Thomas invariance of C3. Okay, and also this magnificent four model, they are related with Donaldson-Thomas invariance on C4. So here are the examples of how this instanton partition function are related to certain interesting mathematical objects. Okay, any questions so far? If not, let me go to our setup, which is mentioned in the title, the tetrahedron instantons. So we say that previously the instanton I mentioned has the setup of D1, D5, D1, D7, or D1, D9 bar. So there's a common feature of all this setup is all this D2, D+1 branes are parallel to each other. So in other words, all this higher dimensional branes, they are supported on the same direction. So then a natural question is, okay, why can we just put this this higher dimensional branes on different directions, or just consider some perpendicular brane setup? So here is our setup for the tetrahedron instantons. So here we have the 10 spacetime. We are working in the type 2b type 2b string theory. So we have 10 space-time dimension from 0 to 9, and then this k d1 instanton d1 instanton so occupy 0 and 9 direction. Then we have 4 different types of D7 branes, which are unoccupied on this on 2 of the directions. And then since we require that all this D7 branes has share 0 and 9 direction with the D1 with the D1 instanton, so we have 4 different types of D7 branes, depends on which direction they occupy. So in this table here, so all the dashed lines means dash directions means instantons are. So the branes occupy this direction, and cross means the instantons are the branes are perpendicular to this direction. So for example, this n1, 2, 3, we have n number of n1, 2, 3 number of D7 brane, which supported on this 1, 2, 3, 4, 5, 6 directions, well perpendicular to the 7, 8 directions. So as the other 3 different type of D7s. So we are so in our setup where we have not only parallel D7 branes, but we have 4 different type of D7 branes, and all of them are perpendicular to each other. So you see that the Donaldson-Uhlenbeck-Yau case, this D1, D7 brane case is just a N000 case, special N000 case in our setup. Well, the magnificent 4 model is related to our setup through tachyon condensation. Okay, so for simplicity, we put this space background in and we put the space time on the flat background, which is R1, 1 times C4. But well, okay. Later one can generalize this C4 to other Calabi-Yau. And to keep supersymmetry, we have to in this case it is necessary to introduce non-zero B field, which are written as which is a 2 form in this form. Okay, and then once we have that, we have the B field with certain value. We actually get a 0,2 supersymmetric effective theory on this D1 brane. So any questions on this setup? Okay, so we call this brain. So now we have a brain setup. We call this brain setup tetrahedron instanton, because in this case we group this 1 to 8, this 8 real space dimension into 4 complex dimensions: Z1, Z2, Z3, and Z4. And we say that we label this each direction as 1, 2, 3, 4 as one of the vertices of a tetrahedron. And then from our setup, we say that each face of this tetrahedron represents one set of D7 branes. So for example, the first type of D7 brane, they are supported on the Z1, Z2, Z3 direction. So they are represented by the 1, 2, 3, this face 1, 2, 3 of the tetrahedron. So every data of this brain setup can be summarized on this organized into this tetrahedron diagram. So that's why we call our setup tetrahedron instantons. So roughly speaking, you can view this branes are sort of related to each face, and then this B field, the components of this B fields are related to each vertices. Okay. And now with this brain setup, we can write down the effective effective theory on this D1s. Again, in the middle, since we have KD1 brane, we have a UK gauge group, and since we have a 4 type of D7 branes, and they introduce each type of D7 brane introduce a flavor group for our effective theory. So in the end, this the strings coming from D1, the strings coming from D1 string gives you a vector multiplate and adjoint chiral multiplate of the gauge group, and then the strings connecting D1 and D7 branes give you a chiral multiplate and Fermi multiplate. So they transform as a fundamental group on the gauge group and anti-fundamental group of the flavor symmetry. But since we have 4 different sets of D7 branes, so we need to introduce this 4 different types of flavor fields, and also this capital B1, B2, B3, B4 adjoint fields are related to the B field in the brane setup we turned on. And then supersymmetry requires that the 0,2 effective theory has the following scalar potential. You see this, it contains 3 pieces of squares. The first one is a sum of B and B dagger plus a phi dagger minus some R times 1. And the second one is some trace of B times phi squared. And the third one is a B commutator squared. The second one is a sum of all different type of B and phi's as labeled here. So basically, if these BI's are related to the each vertices, and the phi I, since they are coming from the D7 brane, they are labeled by the faces. So the second term coming from the vertices, the B corresponds to 1 vertices times the phi corresponds to the antipodal faces. Sorry about my flu. And so the modular space of the instantons, the tetrahedron instantons are related to the modular space of vacua MNK, which are coming from this defined by this B and phi satisfying the relation of y equal to 0, which meaning and quotient by the gauge group, where this this B arrow B are the label of B1, B2, B3, B4, and phi are 4 matrices related to each D7 branes. And then if we impose the condition that y equals to 0, it actually equivalent to the 3 set of different sets of equations. And you see clearly the first one equation is just has the same spirit as the resolved modular the resolved ADHM modular space, right? It's some commutator of B dagger plus B I dagger equal to some resolution term, right? And in the ADHM ADHM construction, there is also this BB commutator term, which looks like the second line of our conditions. But in our case, we just have much more. We have 4 different B's. In the original Nakajima's construction, there are only two B matrix. We have 4 here. So so in our case, we have an extra condition that B and the corresponding phi, this product of B and phi has to be 0. Sorry. Okay, so we call this modular modular space defined here by this matrix by the matrix and relations up to this UK gauge transformation as the ADHM modular space for the tetrahedron instantons. Okay. Yeah. Any questions so far?
So can you say what kind of string gave respectively to phi and B? So they all come from like D1, D7 branes, right? But what is the difference between them?
No, the phi is coming from D1, D7 strings.
Yes, right. Mm-hmm.
It's a B from D1, D1.
I see. But then why they would appear in pairs? So you can pair the B's with phi's, right? Using this tilde notation.
Right. Roughly, that's yeah. Let me see if I can give you a good understanding of why this. Right. Roughly, it's you say it's here. You can so this D1, D7 brings strings. They give you the chiral and Fermi multiplet, right?
Yes.
So roughly, you can construct something something like a phi and then B this term some certain you can have this superpotential term for this for this Fermi multiplet. You can have this superpotential it's called J or this J type or I forgot the notation of 0,2 J term or J term condition. It's something related to this Fermi, and then the other thing is one possible term is this phi times B. So
I see.
So it's a supersymmetric J term that gives you. Then if you since that's a superpotential term, and then it gives you a scalar potential like this b times phi squared.
I see. So, but do you think there's any like string interpretation of this theory, or just from geometry and the brain setup?
That's a good question. I don't have a good answer right now.
Another question is that you mentioned that this is related to magnificent 4 by tachyon condensation.
Right, right.
So at the level of moduli space, what does that actually mean?
That's also a good question. So I will explain certain evidence of this tachyon condensation and this later. So roughly speaking, we think this at the level of modular space, we think this tachyon condensation means taking some fixed point of the magnificent 4 modular space. Later I will show at least in some example that this actually is true.
I see.
Or this at least this makes sense.
Thank you.
No problem. Thanks for the question. So okay, let me first give you some examples of for this modular space. The simplest example is a one instanton. When these b's are just complex numbers. Since these b are complex numbers, then this one of the conditions that the commutator of b's has to 0 has automatically satisfied. And then these phi's are just complex vectors. Then if we just take we only consider there's only one type of D7 branes, right? So these are just one instantons on C3 with a rank n1, 2, 3. Okay, and when we plug in the conditions, the phi 1, 2, 3 is not equal to 0. Then this requires that B has to be B4 has to be 0, and then B1, B2, B3 can be arbitrary. So the modular space in this case is just the sorry. Then the modular space is just C3, which are labeled by this 3 B's, and then this CPn minus 1, which are the relative distance between the D7 branes. Okay, but now if we introduce two type of perpendicular D7 branes, then the modular space actually has the following grouped into 3 different situations. The first one is when this n prime D7 prime branes, they coincide with each other. So so we can treat all this geometrically, we can treat all this D7 branes as a whole. So it just labels so the modular space is similar to the original one, but in this case we should notice that because of this B phi not 0 condition, this D1 brane cannot coincide with all this coincide D7 prime branes. So the modular space, this part of modular space is C2 cross C star cross CPn minus 1. Similarly, if we consider a special case of when D7 branes are n D7 branes are coincide with each other, while this perpendicular D7 branes are separated, we get another part of the modular space as C2 cross C star cross Cn prime minus 1. Then in the last situation, when all the D7 and D7 prime branes are not coincide, they separate from each other, we get the most general modular space C2 cross Cp n plus n prime minus 1. And then the whole, the full instanton modular space union of all these 3 different cases. But now, if we're still using the picture of a thinking about effective series of D7 branes, we have two different, for this n and n prime setup, we have two different point of views. One, we can view this as this n D7 branes are physical brane, and n prime D7 branes are defects in this D7 branes. And the other point of view is will this n prime D7 branes are physical, while this n D7 branes are defects. This potentially gives you certain instantons with defects in different Yang-Mills series, especially when this n and n primes are different. If we look at the word volume theory of this first n D7 branes, we have we have a gauge group as UN, and if we treat this n prime D7 branes are physical, we have gauge group UN prime. So potentially this 1 and 2 viewpoint gives you instantons of different type of gauge theory with different defects. But from the brane setup, we see that this n and n prime, all these different 4 set of branes, they are they should they are equal footing, so there should be there shouldn't be anything special about n and n prime. So this instanton should be the same when we interchange n and n prime. So that gives you the brane setup gives you a prediction that this 1 and 2 setup, although they look coming from different instantons, their modular space should be the same. So our our brane setup actually sort of predict some isomorphism between different modular spaces. Okay, and once we have this brane setup and 2D effective theory, we can also compute the instant partition function from ellipse genus of this as an ellipse genus of this 0,2 theory. I will not go into the details of this computation, but just to mention that there is a part coming from 1,1 string, and there is part coming from 1,7 strings, and all this once we got all the different building blocks, we product them together and integrate over certain parameters. The result is our partition function. So if we put the theory on the 2D, so all these building blocks are actually theta functions. One can compactify the theory on 1 dimension and get 1D theory, and then all the building blocks are trigonometry functions. And in the end, one can further compactify in 0D quantum mechanics, and all the building blocks are rational functions. So we will. Although we have formula for all these cases, it's very interesting that in the trigonometry case, the form of instant partition functions simplify greatly. Originally, you see the computation is a product of certain functions, and then we have to do the integration. We found that in the trigonometry case, the partition function after the integration can be rewritten, and all this all the instantons can be repackaged into this simple exponential form. So we have a simple generating functions for the at least in the trigonometry case, we have a simple generating function for the k instantons in any setup, which is written here. And you see that in this simplified formula, all the dependence of this n1, n2, n3, n4, they coming from this parameter s, which are the product of Q1, 1, 2, 3, 4, with the powers depends on the number of D7 branes. And you see that all these D7 branes enter into this this parameter as symmetric equal footing. So the resulting partition function is naturally symmetric under permutations of these 4 different n's. By the way, I should mention that this generating function for the partition function is a conjecture, but we have tested this conjecture up to very large n and k. So we basically doing brute force computation for very high order of n and k from the elliptic genus formula, and then compare with the generating function we guessed, and we match it to very large n k. But it's also interesting to actually say if we can prove this generating function is true. Okay, so this the generating function for the instanton partition function we found is also related to the M-series index. So suppose we start with 11-dimensional supergravity on S1 cross X, where X is a color B of 5-fold. One can define the M-series index as the following. But it can also be written as some certain plastic exponential like this, where this this generating function fx depends only on the color B of 5-fold. For example, if x is just a C5, this curly f has this form. So our tetrahedron instantons has interesting connections to M-series index, similar to the connection between Gupakuma-Vafa invariants and Donaldson-Thomas invariants. So basically, we conjecture that if we start from some certain M-series index of this C5 quotient by certain discrete symmetry, which we call it some Gupakuma-Vafa site, because since it's coming from M-series computation, and with a certain change of variables, we conjecture that the left-hand side should equal to the instanton partition function plus a certain perturbative part. By perturbative, I mean this part are just a sort of constant without any dependence on this on this k and n. Okay, so one special example is already noticed by Bonini. So it's this C3 cross top knot n, where on the left-hand side, the M-series index is the M-series index computed on the C3 cross C2 quotient by Zn. Well, this Zn acts only on the C2 here. And they found that with a change of variables, the M-series index is the same as the instanton partition function of this of n000 instantons plus a certain perturbative part. We also found that if we consider the color BL as a C3 quotient by ZR times ZR2 times C2, the M-series index can also match with certain instanton partition functions. And we hope to so it's a work in progress, and we hope to finish it soon to match this M-series index with our general formula for the for instanton partition functions. This one. Okay. Right. Let me wrap up. Let's try to wrap up. So here all this thing, all I mentioned is we have some instanton modular space defined from the string theory or imprecise defined by from certain brain setups. Then the question is, what is precisely the instanton we are talking about? What is the geometry or the equations which gives our modular space? So so far we don't have a very good answer to this, and it's definitely worth thinking. So our tetrahedron instantons, there are still two ways of thinking about this. One is we still consider this as instantons on C3 with different defects. Another way of thinking is treat them as instants on C4, but with this effect tetrahedron condensation. Okay, so by our brain construction, we know this modular space is symmetric under permutation of this all different n's. So if we treat them as instantons on C3, we know that this leads to some identification of modular space of UN 1, 2, 3 instantons with this different defects. Okay. So we know that the original, if we specify this N000 special case, which is a K instantons on C3, this ADHM modular space are also modular space of torsion-free sheaves on C3 with chain character N00 minus K. And the geometry can be described by the exact sequence here, where I is an ideal sheaf. Okay, and this okay, so this is the geometric description for the N000 case. So one guess to generalize this is if we have this N1 different type of D7 brains, we may treat this as a D7 brain, defects D7 brain and D1 brain system as described by the exact sequence of 0 to the ideals, and then some certain complex of sheaves and this kind of thing. Then this modular space are just the modular space of this complex of sheaves, which should describe this D7 defect D7 D1 system. Unfortunately, this is just some guesswork, and we don't know exactly what is the exact definition of this complex of sheaves or the things written in the brackets so far. I'm also working with Jie Zhou to find a good mathematical definition for this system. Once, if we have this clear understanding of this thing from mathematics, the permutation symmetry in N's just leads to the isomorphism of different modular space of different complex of sheaves. Okay, and then our instanton partition function gives the generalized Donaldson-Thomas invariance of the modular space of this thing. Okay, so now, well, I go back to Dupei's previous question on this the relation between the modular space and this Hahn condensation. So again, let me show you this as an example of one instanton example. As we mentioned that when instanton number is 1 and then brain setup is n prime 0, 0, we can work out precisely what are the instanton modular spaces, which are written here. But just to recall that you see they have similar, they have very similar structure that for that they have C2 times some CP, some P's. And recall that the modular space of vortices with charge k of un plus n prime gauge group is described by this ADHM construction, and we can show that in this one instanton case, our tetrahedral modular instanton modular space can be written as C2 times 2 fixed point of this modular space of vertices, where this T1 and T2 are two particular U1 action on this big modular space. The details I'm not since my time is up, so I will not go into details of this picking up the fixed point, but the idea is that written this instanton modular space as some sum of fixed point or union of fixed point of some modular space. And in this one instanton case, we can actually work out precisely. And then if we compare the tetrahedron instantons construction and the magnificent four construction, we see that the difference is just the extra condition that the pi and times phi I check equal to 0. So with a similar spirit, like in the one instanton case, we would like to write our tetrahedron instantons as a union of certain t fixed point of the magnificent four instantons. I mean, this is we haven't worked out completely, but I think from the one instanton example, this gives our this is sort of a very promising direction. Okay, I hope this also help answer Dupé's question. And okay, so let me just summarize. So what we call tetrahedron instanton so far is just the system of a normal crossing D7 branes and D1 branes. So they can be viewed as instantons on C3 with some codimension-1 defects. So their modular space, we treat this modular space as the Higgs branch of a 2D 0,2 effective series, which determined by this D1, D7 brane system. And from this 2D effective description, we can compute the instanton partition function as its ellipse genus, and we are trying to match with the M series index. But it's also very interesting to understand, to further understand the modular spaces as invariants of many possible geometric objects. So in the future, we would definitely want to complete our relation between the Donaldson-Thomas side and the Gupakuma-Vafa side. And also, we would like to generalize our computation from C3 to arbitrary to at least more general Calabi-Yau 3. For example, C3 quotient by certain discrete group or toric Calabi-Yau. Especially interesting is when X is a toric Calabi-Yau with compact 4 cycles. And then the other, last but not least, the direction to work is what is the precise mathematical formulation for this tetrahedron instanton? Whether it's some modular space of certain complex of sheaves, or it's a precise some certain fixed point of a magnificent four models remains work in progress. Okay. Thank you very much.
Thanks a lot for this talk. Any questions?
So when you compare the modular space of tetrahedron instanton and that of magnitude 4, you mentioned that one set of equation are different. But then can you see the U1 action from this point of view?
You see that, yeah.
So for example, if I just have like U1 action acting on phi and maybe in some way, would that be a correct proposal for the U1?
So the naive guess would be, since it's all this BIs belong to one of the complex directions, right? One naive guess is just you use this U1 as this U1 rotation inside that that complex direction. This works when, I think this sort of works when this works when in this special case when n prime 0 0. Actually, that's what we found is T1 and T2. But we try to generalize this to arbitrary n and arbitrary k. Well, it seems a very natural generalization, but it just we haven't have a precise argument to get the whole thing. So
you also mentioned that this is related to the ADHM instanton moduli space.
It's a I would say this is a generalization of ADHM instanton modular space.
So either way,